afternoon. In this report, our group will be going in depth about the superstructural design process and elements in a domestic shed. The report will discuss the design process of the columns, rafters and roof bracing. The group were assigned a certain set of shed dimensions and site parameters. We must then adapt the concepts we have learnt in class in order to calculate if the members are both safe and economical. The dimensions of our shed were 12 metres wide, 10 metres long and 5.2 metres high. The roof of our shed also had a pitch of 2 degrees. The other set parameters were a classification B wind region and a wind terrain of category 1. The bracing arrangement was calculated as a group and all members came to the agreement of using the set measurements for the domestic shed. The measurements were clearly set out with a section view and a side view. Firstly, the roof bracing was first analysed. The wind direction was also clearly stated within the figures. To first start gaining information for the overall building stability under wind in the roof and wall bracing, the wind load is to be clearly stated. The serviceability limit state has to be multiplied by the net pressure coefficients, which are positive 0.9 and negative 0.77. The answers are given which result in the pressure and suction for the domestic shed. To gain calculation of the wind load, half of the end gable surface area is needed to be multiplied and divided by the height and width of the domestic shed. The wind pressure for each of the bracing is then found by multiplying the half of the end gable surface area by the pressure and suction of the wind force. Before conducting structural analysis, the kind of section needs to be selected. Slender members, rod bracing, or little rigid members such as angles, hollow cross-section. The slender diagonals were selected because the compressive diagonals are assumed to be a zero force member and all panel shear is resisted by tensile diagonal only. To gain calculation of design forces, the loads are to be divided by 2, which are equaled to 10.64. Each method of section for the bracing is then needed to be found. This is calculated by using the angle of the bracing, the length and the width, the loads, and using Pythagoras to find the final forces applied to that specific bracing. Due to symmetry, only the forces in half of the members had to be determined. After that method, forces in the strut members are needed to be found. This was acquired by using Pythagoras in 3 joints for the strut members to gain information needed. Each joint needed to add the force applied in the bracing members by the force of the wind applied to the bracing. Once finding the answer for 3 joints, once again due to symmetry, only the forces in half of the members had to be determined. Once that is completed, the design forces have been calculated for diagonal members and struts. Then the design of the members using RHS, rectangular hollow section. This will be done by using capacity tables of hollow sections to select cross section for members. Due to symmetry, only the forces in half of the members need to be determined. That concludes the roof bracing, so the wall bracing was then needed to be analysed. First, the south side of the wall is analysed to find the design force is used and multiplied by the height of the structure. That answer, which is 55.33, is then divided by the width of the bracing bracket, which gives the answer of 18.44, which resembles the force being applied onto the domestic shed from the wall. To gain the final answer of finding out what force applied to the bracing, the degrees of the bracing needs to be obtained, which then gets multiplied by the force of wall, giving the final answer of 21.29. The same method is applied for the western side of the domestic shed, which gives the final answer of 24.55. Then, using capacity tables of rod or angle cross-section and select the suitable cross-section.
Today I'll be going through with you the design process of the rafters in a commercial shed. First thing I need to do was find the purlin spacings by using this formula here. The answer I got was 1.82 meters for my purlin spacings. In order to calculate the total G load, I need to find all the elements of the structural shed, how much they weighed. The weights were found in the standards. roof sheeting weighed 7.65 kilograms, which I converted to kilonewtons per meter in order for it to be able to fit in the load combinations later on, as that's all done in kilonewtons and not kilograms. So I had to multiply most of these weights, or that way in kilograms, by gravity and then divide it by 1,000 in order to convert it to kilonewtons. The self-weight of the purlins that we chose in part 1, purlin Z25019, it weighed 0.8 kilonewtons. The weight of the ceiling was 0.25 kilonewtons. The insulation was 0.12 kilonewtons, and the allowance for the services were 0.25 kilonewtons. This was all multiplied by the load width, which was the spacing between the rafters at the center lines. From there, I had to assume the rafter self-weight because these weren't designed yet. I allowed 1 kilonewton for the weight of the rafters. I then had to go into the total load combination, which was adding all of those figures up and getting a total weight of all the acting forces on the member, which was 1.74 kilonewtons per meter. Then I had to find the live load using this formula. This was found in the AS 1107.1, table 3.2. It gave you the formula, but it also said that if the answer that you acquired from the formula was less than 0.25, we had to use 0.25 in order for the structure to be safe. With this value, I got 0.18, which was less than 0.25, so I had to use 0.25 for the rest of my calculations. To find Q rafter was just 0.25 times the load width. My Q rafter was 0.25 kilonewtons per meter. After that, I had to design the wind speed. I had to, using the same standard but table 2.1, I had to find the ultimate limit state. The ultimate limit state was 3.4 meters per second. Serviceability limit state was 26 meters per second. I had to substitute these into the QU formula, and I got results here. I got them in PA, divided them by 1,000, and in order to convert them to kilopascals. I then had to find the net pressure coefficient, which was given in the standards as CP, which was -1 and positive 0.63. These were substituted into formula for P, which was QU times CP, the pressure coefficient. QU was obviously the answers found here. These give you a negative and positive value for the forces acting on the structure, also suction. I got 0.43 and 0.69. I then had to calculate WU, which was the wind pressure. This was 0.43 times 2.5, the load width. And I get, like I said, negative and positive value for the suction. I got 0.6388 and negative 1.725. From here, I had to calculate the critical load width, critical load combination, which was load combination 2. I got 4.713 kilonewtons per meter, and then in order to find the critical load combination for suction, I used formula 5, and I got negative 0.159. Then I had to find the LE in order to select my member. I had to find the M asterisk, which was WL over 8, which was the weight times length over the rafter length. I got 113.112 kilonewtons per meter. I plotted this in the Universal Beams 300 graph, and I selected the member 310 UB 40.4. I had to check for the reversal actions to make sure the beam would be safe in compression and tension. I got 3.816, which meant both the section was safe. I had to check the serviceability using the ES formula. I got 1.79. I had to find the S max to make sure that to be compared to the serviceability limit state to make sure that it was safe. I got 25.9. The serviceability limit state was found in the code, which was the span divided by 300. Therefore, after I used this formula to find the serviceability limit state, I compared it to the S max, and it was greater than the S max, which meant it was safe. So 40 for the serviceability limit state, greater than the S max of 25.9. Therefore, section 310 UB 40.9 was safe and economical for use. Thank you for listening.